President Foster, do you wish to say a few words?
Sure. Thank you, Karen, and thank you all. Welcome everyone. Once again, I'm sure. I wanted to start by saying that it seems appropriate for a gathering and a conference that's focused so much on issues of climate to note that you never know in March, what's today, the 19th, you never know whether March will be acting as a lion or a lamb on a day, and particularly on a Saturday. So I was struck by, especially hearing that you had so many people involved in the conference today and that the attendance remained good. I see there's over 90 people on this keynote right now, which seems tremendous for a Saturday afternoon, because it turns out that March today is pretty much like a lamb and it's gorgeous outside. So please know how grateful I am that all of you are still in here and still hanging in there for this conference. I think that's a tremendous show of support. I also wanted to note that I'm truly a curious person to acknowledge and to be the person doing the introduction today of at this keynote, and really a welcome. And that's because I really know nothing or very little about the topics that you were talking about today. I'm a very late to adopt on technology. I don't know much about it. I'm patting myself on the back that I even got onto this particular session and this Zoom correctly. So I'm really truly that kind of person. I don't know much about how climate works, even though I've become a student of it of late, and I don't know much about how technology works. And it occurred to me as I looked at your program that I would have benefited by spending the day with you, and I would have picked out, I think, a number of things, especially in track 3. I'm into real world applications of anything. I would have looked carefully at track 5, I think, with the education in STEM. I think it was 5. I would have looked again very carefully at history and TCNJ technology. Anything that says TCNJ, I'm kind of drawn to that, and that was number 9. And of course, I would have wanted to learn how to do anything with a ham radio. I think the concept is great, and I would have enjoyed probably spending the day with you. So congratulations on just a beautiful program and a great conference. I want to end by saying that this is really truly a legacy conference. It's a legacy conference for the college. I think, Karen, as you were saying, it's 47 years ago, this conference. It is fantastic to have the broad participation that we have. Want to thank the scholars, the interested parties, the students. I saw Chris Klemps and Maddie Bland are here. Our partners, IEEE at Princeton and others that are partners and sponsors of this program. But I wouldn't be doing my job either as a president or as a colleague without recognizing Dr. Al Katz. You know that he was a founder of this conference 47 years ago. He has been not only an icon at the school, but a tremendous educator. He is beloved by his colleagues and his students. He is affectionately referred to by all of us as really that stalwart educator who is also a philanthropist, who is also an entrepreneur. So he's really the whole package. And he is a person who is generous with his time. He is generous with his students and colleagues, and he has been generous with me. So I do want to give a major shout out to Al, and people can put up their claps or whatever, because he really is someone who is very special for a program such as this. So with that, I know there is someone else here to introduce Bob Kopp. I look forward to hearing Dr. Kopp's remarks, and also thank you all again, once again, for the opportunity for me to say a few words of brief welcome. Thank you.
Karen? Thank you.
Thank you, Dr. Katz. And again, thank you, President Foster, for being here and sharing your observations. We started off this conference with a panel discussion by the New Jersey Department, DEP, and Kate Algarone began by saying that mentioned during her presentation that Dr. Bob Kopp is a world expert in sea levels. We are very fortunate in New Jersey to have someone who is leading in many ways, not only in New Jersey, but nationally and internationally in this area. As I'm sure you all know, He is one of the lead authors of the Intergovernmental Panel on Climate Change, the IPCC 2021 Sixth Assessment Report, which of course was discussed in Glasgow. Dr. Kopp is going to speak on climate, technology, and democracy, and we warmly wish you here. Wish you welcome.
Great. Well, thank you, Karen, and thank you, President Foster, for being here as well. So let me just get my slides started, although I actually just want to start. And thank you, Dr. Katz, for having organized this for 47 years. I think the theme of legacy that President Foster raised is actually very much how I was sort of thinking of this as well on multiple different scales. So when Karen and the other organizers of TCF reached out to me to speak today, I had a reaction somewhat like President Foster, who obviously speaks because of TCNJ's important work hosting this conference. But I confess I was a little puzzled. I'm a climate scientist. I'm not a computing expert. So I wondered what I had to say to a computer festival. And Karen explained to me that TCF wasn't just a computer festival, right? It's a technology festival. So what's technology? The dictionary definition is that technology is the practical application of knowledge, right? So it's almost saying technology is civilization. And by that definition, of course, human-caused climate change is certainly a problem both created and in part solvable through technology. But that definition is so broad, I thought best to limit myself to the context of that's primarily defined TCF over its years, namely electronic and computing technology. And I realized that though I'm not a computer scientist, a climate scientist, and not a computer scientist, not a computer engineer like Dr. Katz, I wouldn't be where I am today had I not been a kid who would have loved to come to TCF when Dr. Katz was just getting started, when it was in its first couple of decades. So this is a photo of me during TCF's first decade. And I wouldn't be the climate scientist that I am today had I not been this preschooler fascinated by our brand new IBM XT clone, which you can see over there on the left, and our Commodore 64. Had I not been an elementary school kid who learned to program BASIC on an Apple IIc Plus, which somebody who's now a librarian has brought to our house on his backpack. Had I not been a middle school kid who got his first email account through the Capital Area Public Access Network, or CAP Access, which I'll talk about again in a bit. And had I not been a high school student who used Linux and read /dot obsessively. So I'm certainly of the community that I think TCF was targeting when I was the age that I was developing into who I am today. Had I not been that kid, I wouldn't have ended up on a research trajectory that largely involves using statistical and computational models to understand the planet's past and future and to help inform decision-making about our collective future. And so reflecting on TCF's legacy and its relationship to my own history, I accepted this invitation eagerly. So let's get to the climate part of it all. And I want to start with some context. I know many of you have been sitting through climate talks over the course of the last several hours. And so this will be familiar to you, but I want to get everybody on the same page. We have from ice cores very good records of the composition of our atmosphere over the last 800,000 years. So we know that for the 800,000 years before the Industrial Revolution, carbon dioxide and the concentrations oscillated in a fairly narrow range between about 180 parts per million, which you can see as these low numbers on the plot, during periods we called ice ages, and around 300 parts per million during warmer periods that we call interglacials. In 1913, carbon dioxide concentration surpassed 300 parts per million. So it surpassed the bounds of the last 800,000 years. In spring 2014, they surpassed 400 parts per million for the first time in probably about 3 million years. And in 2021, they averaged about 417 parts per million, nearly 50% higher than they were at the start of the Industrial Revolution. So let's look at this in a little more detail. Sorry, I'm just rearranged a couple of things here. In 1750, before the start of the Industrial Revolution, carbon dioxide concentrations in our atmosphere were around 277 parts per million. Over the next century, they rose by about 10 parts per million to 287 parts per million, primarily as a result of coal combustion. Over the next 50 years, they rose by a similar amount, reaching 296 parts per million in 1990. And over the next 50 years, rose a little bit more to 311 parts per million in 1950. Then in the post-World War II era, we see a dramatic acceleration. By 1988, carbon dioxide concentrations had risen to 351 parts per million. And over the subsequent 33 years, it rose by another 66 parts per million. So about as much since 1988 as in the prior 133 years. And so this is important because it's natural to fall into the habit of saying climate change, anthropogenic climate change is a problem caused by all of human activity since the Industrial Revolution. But really, most of the increase in carbon dioxide concentrations that's driving the changes we're experiencing today has happened since the late 1980s, since I was that elementary school kid learning to program on an Apple IIc+. Sorry, there we go. And the reason for this is simple. Most of the carbon dioxide ever emitted by burning fossil fuels has been emitted since 1991. Let's look at this. So, but this plot is showing you cumulative fossil emissions. So when we see a number here, that means, for instance, this number is 1850. That's the total amount of carbon dioxide emitted by burning fossil fuels between 1750 and 1850. That was about 5 billion tons. Between 1750 and 1900, around 45 billion tons. 1750 and 1950, around 230 billion tons. So by 1991, cumulative emissions had reached 830 billion tons. By 2020, they reached almost 1,700 billion tons. So again, right, we can think of this as the legacy of the Industrial Revolution, but really this is by and large a problem of the post-Cold War period. As a result of all of these emissions, our planet is running a fever. So this plot here is showing you the temperature increase since 1880. Many of you have probably seen versions of this before. Between 1980 here and 2020, temperatures have risen at an average rate of about 0.2 degrees Celsius or 0.3 degrees Fahrenheit per decade. And the last 7 years are most likely the warmest 7 years on records, with temperatures now being about 2 degrees Fahrenheit above the late 19th century average. So climate change is no longer an issue for the distant future, as it might have seemed when TCF was getting started. As I'm sure you all know, it's already affecting people across the world. And using computer simulations, it's now possible to rerun weather events and ask how they might have played out differently had it not been for those extra 2 degrees Fahrenheit of global warming. And here are some examples of what these analyses have found. So heat. This is one of the easiest things to tie to climate change because the physics is pretty simple, right? We're trapping more heat on the planet. So when a heat wave happens, it's more intense, it's hotter. And so one of the early heat wave attribution studies, this area is called attribution, found that the 2003 European heat wave, which killed about 70,000 people, was about 3 times more likely as a result of the climate change that had happened to 2003. And had it not been for that human-caused contribution to climate change, there would have been about 2/3 fewer deaths during that heat wave. Since 2003, the probability of that event has happened again. It became about 3 times more likely over the following decade and has continued to rise since. Another thing we can talk about when we talk about the effects of climate change. When you turn up the temperature of the planet, the atmosphere holds more water vapor. And when the atmosphere holds more water vapor, you get more intense precipitation. So this is a photo of flooding in the Houston area after Hurricane Harvey. This is an area that has been the subject of these sorts of simulations. And what they suggest is that Hurricane Harvey's intense rainfall, which in some places reached more than 50 inches, was made about 3 times more likely as a result of climate change. Now, I think many of you, like me, are in New Jersey. You might remember Hurricane Ida's flooding back in September. This is a photo of Route 18 near the Rutgers New Brunswick campus. And I haven't seen studies similar to that, which was done for Hurricane Harvey, for Hurricane Ida here in New Jersey, but we don't really need them to make the point. Right? We know from basic physics that when you turn up the temperature, you trap more water vapor, you get more intense precipitation. And so we can say quite confidently that the flooding we experienced back in September here in New Jersey was made more intense as a result of climate change. My personal experience, our basement flooded for the first time since we've lived in this house during Hurricane Ida. Not a lot. We had neighbors who were much worse off. But because we were on that cusp, because we got a couple of inches of flooding in our basement, I feel pretty confident saying that our basement flooded because of climate change. Had it not been for that extra intensity of rainfall, we would not have experienced that intensity of flooding. What are some other things we can attribute to climate change? So droughts, particularly the temperature-driven portion of droughts, the fact that you get more evaporation because of the heat, that can be fairly confidently attributed to climate change. This is a photo from the Western drought in 2015, and of course there's ongoing drought, the super mega drought there now. And here in New Jersey, we're also seeing, and around the rest of the coast of the US, we're also seeing the effects of sea level rise. The sea level rise is making high tide flooding more common. It takes a less extreme high tide to cause what's sometimes called nuisance flooding, as you can see in this picture from a high tide in Ventnor, New Jersey back in 2017, where roads are flooded. The number of high tide flooding days in Atlantic City have increased from less than 1 per year in the 1950s to an average of over 8 per year in the last decade, a period over which sea level rose in Atlantic City by about 9 inches. And when we get storms, when we get the intense flooding associated with storms, it's more intense as a result of those extra inches of sea level rise. So together with partners at Climate Central in Princeton, we've done a study looking at the human contribution through sea level rise to flooding during Hurricane Sandy. And what we found is that human-caused sea level rise was responsible for about 13%, or $8 billion of the property damage caused by Sandy in New York and New Jersey. And that about 70,000 people were affected by Sandy's flooding who wouldn't have been affected had it not been for the human contribution to sea level rise in our region. So that brings me to our next point. Every additional amount of greenhouse gas we emit into the atmosphere makes climate change more severe. And in fact, we can quantify that. Roughly, we get about 0.4 degrees Celsius of warming for every trillion tons of carbon dioxide we put in, which means that at the current level of emissions, we're getting about 0.2 degrees Celsius per decade of warming. So that means that a key driver of the range of possible climate risks we face and might have to manage is the range of possible human emissions. So it's something that is under our collective control. And it also means that in order to stabilize the climate, in order to prevent the problem from getting worse, we have to get global net carbon dioxide emissions to zero. There is no level of net carbon dioxide emissions that are consistent with a stable climate. So I want to tell you some stories about our possible futures. And in that theme of legacy that President Foster laid, the legacy that we're going to leave to the next generation. So as I said, a key driver of the range of possible futures is the range of possible human emissions. This figure here is showing you carbon dioxide emissions starting in 1960. And I want you to think back first to the 1980s, when I was learning my way through BASIC and Al Gore was convening some of the first congressional hearings on climate change. Each year, humans were pumping about 20 billion metric tons of carbon dioxide into the atmosphere by burning fossil fuels. And since the start of the Industrial Revolution, we had emitted a cumulative about 600 billion metric tons of carbon dioxide from fossil fuels, which together with emissions from deforestation and together with other greenhouse gases raised global average temperature by about 0.4 degrees Celsius or 0.7 degrees Fahrenheit. So let's imagine, suppose we had had a policy change. And starting in, say, 1992, which was the year when international climate talks first began, we had gotten carbon dioxide emissions on a downward trajectory, a trajectory something like trajectory A shown here. We could have had about 90 years to get global emissions to zero and still had a good chance of stabilizing the climate at well below 2 degrees Celsius, which is one of the international goals agreed to in the 2015 Paris Climate Agreement. This particular trajectory shown here would have led to about 1.8 degrees Celsius of warming with a range of about 1.3 to 2.4 degrees Celsius. Now that's about 3 degrees Fahrenheit with a range of 2 to 4 degrees Fahrenheit. and would have stabilized at that level by the end of the century. But we didn't get on the future. This black curve is our historical trajectory. Instead of getting on a downward trajectory when we started these international talks, carbon dioxide emissions continued climbing. And now nearly 40 billion tons of fossil carbon dioxide are emitted into the air each year. As a consequence, the planet's temperature has increased by about 0.8 degrees Celsius since the mid-1980s. And we are feeling the consequences that I talked about earlier. So let's talk about another future. What 15 years ago, we might have called business as usual. If over the last decade, emissions had continued growing at the same rate as they did in the prior decade, we would be on something like the trajectory I've drawn here as future D. On this track, we would most likely have been headed for about 4 degrees Celsius, or 7 degrees Fahrenheit of warming by the end of the century. Fortunately, that's not the trajectory we're on. It hasn't been for the last decade. Emissions growth has been slowing as a result of a combination of policy and market forces, particularly the uncompetitive nature of coal in many places and the rapid declines in price of renewable energy. So this is important to realize. We may not have had an aggressive policy that many of us would have liked to have seen, but there has been a lot of progress. In the US, for example, the Clean Power Plan, which was the Obama-era plan to regulate carbon dioxide emissions from electricity, was stopped first by litigation and then by reversal during the Trump administration, and it never went into effect. But we have already met, as of 2020, the emissions reduction goal for the electricity sector that the Clean Power Plan set for 2030, right? So we are making actually quite good progress in the US by chance, and that chance keeps some options alive. So now it is still possible to achieve the Paris Agreement goal of limiting warming to 2 degrees Celsius. But instead of getting to 0 in 90 years, we have to get there in about 30. Alternatively, as shown in the pathway shown here, which is one of the illustrative pathways that climate scientists like to use, we could take a little longer, as long as we are going to count on technologies later in the century that are going to allow us to actively pull carbon dioxide out of the atmosphere, whether that's by extensive forestation or extensive deployment of new technologies, or most likely a combination of the two. So future B, allowing us to keep those Paris Agreement goals on our current trajectory, is not as easy as it would have been had we started in 1992, but this would still be a pretty optimistic future. And this in yellow here, that's future C. That's closest to our current policy, which puts us on track for almost 3 degrees Celsius of warming by the end of the century, about 5 degrees Fahrenheit. Now let's talk back about legacy again. When I look at projections for the next 80 years, I think of my son, who's about the same age as I was in that photo I showed you at the beginning of the talk. I hope he'll be in his 80s and still around at the end of the century. So this is his life, right? Are we going to be on future B or future C? Whichever course we're on is not going to affect how much the climate changes over the next decade. The benefits of reducing emissions in the climate are really going to take until the 2030s to start to accrue. But nonetheless, 2030 is going to look very different in future B and in future C. By 2030, it'll be clear whether we have managed to turn a corner. In future B, the green future here, the urgent calls for climate action that you've heard earlier in the day will have made an impact. So we'll have to see massive infrastructure changes that will have led global emissions to have fallen substantially over the next 8 years. In future C, on the other hand, policy inertia will keep emissions roughly around their current level. Clean energy technology will continue to progress as it has been quite rapidly, but it will not be enough to drive systemic change, and the Paris Agreement goals will become increasingly out of reach. By the time my son turns 40, the same age I am today, the two climate futures will markedly differ. In future B, we'll be seeing large-scale investments in a booming carbon-free economy that will have put us within striking range of net zero carbon dioxide emissions and global climate stability. Nonetheless, heat waves, flooding, wildfires will still be worse than in 2020 or 2030. And the oceans will still continue to rise for many centuries to come. But we will have gotten ourselves enough time to develop the systems to manage the elevated risk, and we will have stopped that risk from continuing to get worse. And future C, emissions will have continued at around their current level. Temperatures will be blowing past 2 degrees Celsius with little slowdown in sight. And the impacts on climate change, on human health, on agriculture, on energy system, on economic growth, on violent conflict, and on many other aspects of life will continue to worsen and will fall disproportionately on the poorer parts of our country and the world. So now I want to get you to the first technology part of the talk. What's the relevance of computing technology? Well, one of the things computing can do is help us see the choices we face. So I want to take a few moments to tell you a little bit about our work. And I know Karen mentioned my work on sea level rise. That's actually not what I'm going to focus on here. Instead, I want to focus on a collaboration that we're involved in called the Climate Impact Lab, which is a partnership between our group at Rutgers and colleagues at the University of Chicago and Berkeley in the Rhodium group that is focused on using big data, using modern statistical methods, and using state-of-the-art climate projections to assess the economic risks that human civilization faces as a result of carbon dioxide emissions and climate change. So our team works on a lot of different types of impacts. So we've spent the last several years working, for instance, on mortality, on the heat and cold related deaths associated with the climate, on agriculture, on energy, on labor, on coastal damages. And we also have some work on looking at things like civil conflict, crime, and migration. And I want to give you just one example of how technology allows us to look at these. An example of our work on heat and cold related deaths. So how do we go about developing these data-driven estimates of climate impact? So step one is to assemble lots of data. So this map here is showing you where we've assembled data for our human health study and the time periods the data covers. And so in order to do this, we have to start by assembling what we believe is the most comprehensive and self-consistent set of subnational, that means sort of, county or state level mortality statistics in the world. So step two is to use statistical methods to learn how weather relates to the impacts we care about across different regions and climates. So we take all that health data that I showed you in the previous slide, we link it to daily climate data over the last 40 years. And we say, okay, how much does a day of a given temperature affect mortality rates over the course of a year in a particular county? So from that, we can learn that the effect of a hot day, so this is showing you a 35 degrees Celsius day or a 95 degree Fahrenheit day in a given part of the world, is not the same around the world. It differs a lot, and it differs because of two factors. It differs because of income, so wealthier areas have a different susceptibility than poorer areas, and it differs because of climate. Areas that are used to very hot days are more adapted than areas for which it's rarer. So what we see is that death rates are largest in places that are poorer or are colder. So within the US, for example, Houston is less susceptible to deaths as a result of extreme heat than, say, Seattle. And that's because Seattle has invested less in technologies like air conditioning and changes of practice to deal with extreme heat that is sort of typical summer experience in Houston. And also we see places in Africa and other low-income parts of the world are more susceptible than wealthier parts of the world. So we learn about the relationship between temperature and climate and mortality. And then we project those futures. So we use state-of-the-art climate models to explore the range of local climates that are associated with a single emissions future. Right, recognizing that there's a range of global temperatures that could result from our emissions trajectory. So although I said sort of that future B is 1.8 degrees C, I noted that there is a range of around 1.3 to 2.4 degrees Celsius. So every emission scenario is a gamble, right? We might be currently on a trajectory that's sort of roughly 3 degrees, but we can't rule out that the same trajectory would get us to 4 degrees. And so we have to look at those range of different futures and also how those range of different global temperatures translate into different local temperatures. So we use climate models for that purpose. And then we combine those to project future impacts and costs. And so this here is showing you the costs of both the human health impacts and the cost of adapting through, for instance, buying air conditioning as a result to limit those impacts. So you can see here that in some places, the colder, wealthier parts of the world, the effects on human health are actually beneficial on net, even though people will still be dying during heat waves in these regions, and that they're really concentrated in areas that are lower latitude and lower income. And so this is showing you the cost of mortality in that future C. And it's an example of a tool we have on the Impact Lab website, impactlab.org, if you want to check it out. And that tool will be expanding over time to include a bunch of different impacts. But in general, what we learn, and this is true across different types of impacts, that people in low-income countries die from climate change. Those in wealthier countries largely spend money to adapt. So it's costly to us too, but it's costly to us in the US largely because we will spend money to avoid a lot of heat-related deaths. So as I said, we're working on a bunch of these different impact categories where there is behavior we can look at in the past that can help us inform what our projections of what happens in the future. But we have to also recognize the limits of this sort of technology-driven approach, right? Though we can make robust conclusions about many types of climate impacts, big data cannot tell you about impacts that represent a break from past behaviors, right? So if the accumulated effects of, say, seeing heat waves more and more frequently on society is not simply the effects of each of those heat waves individually, but lead to more social stress that lead to changes overall in society, to social tipping points of one way or another. You can't learn about that through this sort of data-driven approach. So now the democracy part. We have to make collective choices about how to lower our emissions, and regardless of how much we lower our emissions, we have impacts that we have to adapt to. So we also have to make choices about how we're going to adapt to changes we don't avoid. And yet, even with the climate we have now, we aren't working together in the US very well to manage our climate risks. So think back to Hurricane Maria, September 2017, right? Talk about in Puerto Rico, the storm destroyed us, as this New York Times headline put it. Well, a century later, the New York Times headlines was, on Hurricane Maria anniversary, Puerto Rico is still in ruins. In 2019, the US House approved disaster relief and Puerto Rico aid over the president's objection, and then it gets delayed again. It gets delayed again, and finally, in 2021, there is still funding that was intended for Hurricane Maria relief that has not been delivered to Puerto Rico. This is not the sign of a governance system that is that is acting in terribly responsive ways to manage climate risk that we face now. And there's no app for resolving that. While technology is extremely helpful in helping us see our problems, it can't solve our problems. It can't tell us what we should value, though it may help us see how the consequences of different decisions either support or work against our values. So strategic, value-informed decision-making has to emerge from people and their deliberations. And if we value democracy, as I hope everybody here does, if we value the idea that all people are entitled to their say, then we need institutions and technologies that support participatory democratic dialogues around these hard choices. So technology could help build community and strengthen democratic decision-making. That was a vision of some of the early pioneers who popularized the internet. I mentioned, for example, in sort of my own personal history, the Capital Area Public Access Network, CAP Access. I want to read you a little excerpt from a paper that team that developed CAP Access released describing their vision and the vision of the movement they were part of. At the outset, they wrote, the Freenet Bulletin Board software Freeport was developed at Case Western and was made available for $1 a year, so long as it was used for free non-commercial purposes. And an umbrella organization, the National Public Telecommunications Network, was created to organize these new free nets, attempting to recreate for public networking what the public broadcasting community had done in television and radio, and to imbue it with all the sensibilities that have justified and sustained the nation's public library system. A wealth of parallels appealed that suggested that something called public networking would be the next plank and the information and participatory flooring that undergirds democratic public enterprise. So that was a fairly expansive vision in the early 1990s. Now think about what we have today. Facebook's mission statement sounds maybe similar: to give people the power to share and make the world more open and connected. But notice there is nothing there about the end to which they are making the world more open and connected, or what sort of sharing they expect. And what do Facebook and their similar services actually do, regardless of what their mission statements are? What's their business model? Their business model is capturing and selling users' attention. And they direct that attention towards what makes them profit, not towards the problems we need to address collectively. So I think we've taken a path that has led us away from this idea of public networking to support democracy, and instead ended up building our social infrastructure on technologies that are really about capturing our attention and selling it. Both to limit and adapt to climate change, we need responsible democratic governance. And that means that technology people, you all, need to help us achieve our public goals, not just private profit. For those of you who aren't aware of it, I want to draw your attention to, I think, some exciting work going on in this area by groups like the Center for Humane Technology. We have a list of what's wrong with the social technology we have now, right? We have social technology that doesn't support democratic deliberation. It makes the trivial seem urgent, at the same time that we actually have these urgent problems, right? We were talking about, right? The world is going to look very different in 2030 in future B or future C, and that's going to have substantial implications for the climate risks we face over the longer term. We have technologies that encourage seeking without fulfillment, that force us to multitask rather than to focus on these hard problems, that weaponize fear and anxiety, that encourage constant social comparison, and that tell us what we want to believe. None of these are things you would want built into a technology that was designed to support hard democratic deliberation. So what can you do? I know I'm not the only person today to charge you with things to do, but I think I want to ask you to consider being active citizens, not just by talking to your congressman, although that's great, not just by voting or following national politics, although that's really important, but also in your local, state, and work communities as well. And these photos here are two examples of stuff we're doing at Rutgers that are very much in this spirit. So on the left, this is a photo of some work we're doing through a variety of projects focused around helping communities have science-informed discussions about how to adapt to climate change. So the most recent iteration of that is a project we launched last year together with 11 other universities and funding from the National Science Foundation, called the Megalopolitan Coastal Transformation Hub, which is about understanding how changing climate hazards interact with household decision-making and the markets and municipal decision-making and finances to shape the effectiveness of different adaptation pathways, and using that to help our communities prepare better. Over here on the right, we're showing you pictures from another process that we spent the last 2 years doing at Rutgers, just developing a climate action plan for the university. And one of the things I do now is co-lead something called the University Office of Climate Action, which is focused not just on helping Rutgers achieve its goal of achieving carbon neutrality by 2040 and becoming more resilient to climate change, but also on leaning into our role as a public land-grant university of New Jersey and helping New Jersey more broadly foster sustainable, climate positive, equitable economic development. We've adopted this as a top level priority for the university, and it involved a lot of deliberation, and it will involve a lot of consistent and continual engagement with people across the state to get there. But I think it's really important role for public institutions, particularly long-lived public institutions like universities, to play. So this is the hard request for you. Think about the ways you can be active in your local, state, and work communities and become engaged, and make sure we're having these conversations about climate. And if you're a technology person, think about whether the technologies you're making are fostering democratic deliberations or working to take our attention away from the problems we need to solve. And I want to give you something fun and less hard to do. If you're a homeowner, and even if you're a renter, one of the things we need to do over the next decade is decarbonize the nation's infrastructure. And particularly if a homeowner, there's a bit of the nation's infrastructure you have direct control over, which is the things in your house. And I want to draw your attention to this group, Rewiring America, and their guide, which has a really useful guide around all of the things you can do to get to the point where you're going to be able to transition your house away from being powered by fossil fuels. And this is sort of, I would say, a fun technology project, electrical technology project to lean into that perhaps balances the sort of hard work of being active citizens that I've also asked you to do. So thank you. I look forward to the discussion.
Maddie, who's the president of the IEEE students for New Jersey, I believe. Do you have the questions in the chat?
Yes, it looks like there are a few questions. So we have the first one from Brenda Bell. Dr. Knopp, I don't know if you want to look at them in the chat and then answer them.
Sorry, I thought you were going to synthesize them for me. I can take them from the chat if you'd prefer.
Awesome.
Okay, I'll take them from the chat. So Brenda Bell asks, one of my big questions relates to how climate changes relate to climate changes on the geological timescales. That's a great question. Of course, I showed you that context over the last 800,000 years, where the warming between an ice age and an interglacial period is about 5 degrees Celsius. So, the choice between future B and future C is between about 1/3 of an ice age transition and 2/3 of an ice age transition in the other direction. The pace of the changes we're seeing in climate is extremely rapid. And the best estimate is that it's maybe the fastest in at least 55 million years, and possibly since the impact that killed the dinosaurs. So we're seeing very rapid change, and we're seeing a change that is on the scale of these glacial interglacial changes, but those glacial interglacial changes take tens of thousands of years. So Joseph Jessen is asking a question about the acre of green forest. That's how much carbon dioxide that can absorb compared to an average car's annual mileage. There's a lot there's a lot in that question. Green forest, it depends not on how big the forest is, but how fast it's growing, how much carbon it's sequestering. And so I can't give you a number in that. I'd have to actually look at the numbers. But the basic thing is that, right, it's growing forests that capture carbon. It's cutting down forests that leads to decomposition and the release of carbon. And currently we are emitting about 5 or 6 billion tons of carbon dioxide a year through deforestation, and ideally we would like that number to have the opposite direction so that we're net capturing. IE Fabi B is asking about uncertainties in big data forecasting. Yes, that's very important. All statistical analyses should give very careful certainty to the numerical results. If you go to the Impact Lab map I showed you, you can look at the 5th and 95th percentile of our projections, but you can also learn what are robust findings, right? And the robust finding is that, basically lower income people have to suffer the impacts of climate change, and wealthier people have the resources to spend money, which is still costly to them. Let's see, what are other questions? So technologies used to generate electricity for the electric home school company. Well, so let me talk about the rationale between why I say like electrification is an important priority, right? It's because the easiest thing to decarbonize in our country is a grid, right? It is quite possible for us to get to a net zero carbon grid by 2035, which is the Biden administration's goal. So if you electrify, what it means is that your emissions, rather than being locked onto, say, having to burn gas because that's what the furnace in your house uses, gets to decarbonize along with the electric grid. And so, things like replacing your furnace and your boiler with a heat pump and a heat pump water heater, like those are the two biggest things in your house. Electrifying your vehicle being the third big thing. And so once you've electrified those, here in New Jersey, we have a relatively clean grid. Roughly half the electricity comes from natural gas, which is cleaner than coal, and half of it comes from nuclear, which is zero carbon. And as the grid transitions to being 100% clean electricity, right, the emissions associated with using that will go away. There are other technologies that are fun to interface with, but are actually more important from a human health perspective than the emissions perspective. So that's particularly things like replacing that natural gas stove with an induction stove. Turns out that particularly if you don't have a fume hood over your natural gas stove, it's really bad for your health. And if you have young children and you don't have a fume hood over your natural gas stove, I would encourage you to prioritize doing that. But those are sort of the core suite of technologies, are heat pumps and heat pump water heaters and electric cars will get at the largest chunks of emission. Are there other things that have changed in the last 40 years that increased US energy use? Well, US energy use, per capita has not increased that much, but we're a much larger country than we were 40 years ago. We also have bigger houses. And so, those have offset the fact that we're a larger country and we have more house space. Those have offset the fact that there have been substantial gains in efficiency over the last 40 years, right? If you look at energy intensity curves, right, the amount of energy it takes to produce units of GDP, there was actually a bit of a climb for many things up until the 1970s, and then there's been a decline since then. It just hasn't been enough to offset the fact that there's more of us and we have more economic activity.
President Foster, do you have a question?
Yeah.
Yes, I did. And it's going to go to the democracy part of your talk,
yeah.
Bob, because that's where I can come in, and I suppose on the others. And so I was thinking, when I looked at the maps from the lab, it's clear that there's differential impact, and it's clear that different areas and communities will be affected differentially by what's going on now in the future. And so I got thinking about democracy idealized, yes, absolutely, but politics, no, right? Because you have this cautionary tale of Puerto Rico in your talk, which is about the fact that it's hard to care for somebody else. When my roof isn't leaking, I don't care about somebody else's. And so for me, perhaps more of a comment, but you were saying, what are the things that we could individually do? But there are also things that we need to collectively do. And it will take a tremendous amount of spine and commitment from elected officials and others, people advocating for that, to make the changes in the sphere, if you will, of democracy, to create the foundation for us to move forward with some success. So although there are technology and sort of scientific realms to play with, from my perspective, it's a governance realm to play with as well. And it could be moral suasion, it could be game theory. I don't know what all those plays are, but I will say that right now we don't seem to be there. We're like, well, why should I bother to get my electric vehicle? It's a little inconvenient now. Or why should I care about what's going on in, I don't know, some other part of the world, because whatever. So I'm blathering a little, and I don't mean to do that. So I'll just simply say that the political or the democratic side of this struck me as extremely important.
Yeah, no, I absolutely agree with you, right? I mean, look, we can just look at how we've responded as a nation to COVID and the failures of governance there, and the way that what ought to have been, a collective process that was informed by science sort of has turned into this polarizing political process, right? I think that I hope I leave you with a somewhat hopeful message. But the grim part of the message, I think, is, we know how to solve this problem on a technical scale, but I don't know that we can solve it if we can't solve the broader problems of polarization and democratic lethargy. What I can say too is, so the reason why I said, don't just focus on national politics is that I do think it is more possible to do a lot more at a more local communities, and it's not enough, but I think that it has to be the step to fixing our national discourse, right? So that's why, like, I've spent a lot of time over the last 2 years thinking about Rutgers and our role as a 100,000 person community within New Jersey, and our role as a public university with a public mission, and how we can help catalyze other activities at a community and state level, because I think I see how I can get leverage there. But yeah, I mean, I think there's a lot of factors that drive our polarization. Technology is not the only one, but I do think it is contributing. And I think that our ability to tackle climate change is ultimately, it's a question of governance. It's not a question of technical feasibility or even economic feasibility.
Yeah, thank you. I appreciate that. I also appreciate the COVID analogy, scary as it is. Yeah.
So I know we're at 4:30. I don't know, Karen or Madison, if you want to, I can stick around to take a couple more questions, but I don't want to keep people. So you want to.
We're open here time-wise, so you don't need to, as I said, usually we have in the time before COVID, we'd have an open period where the keynote could talk to people on a one-to-one basis, and then we'd all go to a banquet, but that's not going to happen this year. So we aren't getting kicked out of here. Maybe we should put a limit on this and say.
All right. Well, so maybe it's like we can, see what let me see what else that people have asked about in the chat, and also people want to raise their hands and ask questions. That's fine too. Questions about direct air capture. There are a bunch of direct air capture technologies that have been proposed. They're all costly. I'm not sure I could tell you which exactly are the most promising, because it evolves relatively quickly. When we say I am concerned, as many people are, to look at these, look at scenarios which require globally negative carbon dioxide emissions to stabilize the climate, because that's a huge amount of infrastructure. I mean, if you think about like that, the particular version of Future B I showed you took until about 2070 to get to net zero, and compensated for that by having negative carbon dioxide emissions after that are of the scale of about 1/3 of our current emissions today, right? So if you think about, like, if you're really counting on that, like, you're going to need infrastructure that's a substantial fraction of the scale of our fossil fuel infrastructure to achieve that. That's a huge infrastructure that we have no idea whether it'll work. And so if you were a more conservative person, you would say, well, you probably don't really want to count on having, so much direct air capture available that we're going to be running globally net negative emissions for a long period of time. And so that would point you more towards, if you really want to achieve the Paris Agreement goals, you want to get to net zero by around 2050. So Hawaii, I don't know a lot about Hawaii in detail, but I mean, I think one lesson to take away from Hawaii and why they have been ahead of the first with electrification is that if fossil fuels are expensive, you have more incentive to not use them, right? That's sort of market economics 101. Right, and the rationale behind what some of the previous speakers were talking about focusing on carbon pricing as a key tool. Of course, we can only look at what's going on now, recognizing that people are very sensitive to the rising prices of gas, even if they're also very invested in us supporting under siege democracy in Ukraine. And the political tensions you see associated with that are going to be the same political tensions you see if you're using a carbon price to change behavior, particularly if it's affecting gas prices. I'm trying to look for questions that are sort of precisely enough phrased that I can answer them quickly, but I think some of these require somebody else, some of the speakers to ask their questions a little bit more directly. So yeah, let me, there's a couple here I want to take on. So Neil asked there, by 1965, there were credible reports that carbon dioxide would be a problem. What do you think will convince enough deniers that we can reach a point where we can agree to take comprehensive steps? Well, that gets us back to our democracy question, right? 67% of Americans support strong action on climate, which if we had governance structures that translated strong majority opinion into political power, means that we would have, we would be making the investments to do that at a national level. So I think the question is, we have to solve the democracy challenge that prevents policies that have 2/3 support from turning into federal policy. So I don't think it's really a matter of convincing deniers. It's a matter of, addressing the governance challenge that has created this, sort of political paralysis at a national level. And President Foster just popped up. I don't know if she wanted to add on to that, or that was just a coincidence.
No, Bob, that was great. Thank you. That was my comment as well. Thank you.
Let's see what else was here. Yeah, if more heat pumps, air conditioners are being installed, is there any consideration of potential effects of refrigerant being leaked to the atmosphere? That's a really important one to address. So first of all, of course, I think most people in the US already have air conditioning. So when we talk about heat pumps, the minimal policy, ideally what we want is basically, let's just make every air conditioner a heat pump. That might not be quite as fast as we like, but if people stopped installing new air conditioners that also couldn't serve as heating units, you would rapidly expand the number of heat pumps that were out there. But yeah, HFCs are an important contributor to the greenhouse gas emissions. They are being phased out under the Kigali Amendment to the Montreal Protocol. The Montreal Protocol, is what originally banned CFCs, and is one of the the best examples of functioning international environmental governance. And so, yeah, I actually have a house that had, we bought 4 or 5 years ago. The previous owners had installed a heat pump. I think they were we had just been installed basically as an air conditioner that happened to also be a heat pump. It's having some issues, but we're actually trying to keep it going long enough because given the option, next year is when these non-HFC heat pumps are going to become more widely available in the US market, and the HFC ones are going to be phased out. So given that I have one already installed, and don't need to replace my, I would not right now replace, say, a furnace with a heat pump if the furnace wasn't broken, because I actually think waiting a year until those are available would be useful. But what you want to do, right? Most people replace furnaces or boilers under time pressure, right? You basically don't think about them until they break. And that's the big challenge there on the electrification side, right? You want to have thought about this in advance so that when your heater stops working, you know exactly what to do. Or when your hot water heater stops working, like you've got the plan in place. Maybe you do it preemptively, but I do think that the HFCs are a concern and are being phased out. So I think those are. Craig wanted to ask, what actions are we taking at work? Well, so I now have a role co-leading the Office of Climate Action at Rutgers, which is responsible for holding the university and its 100,000 person community accountable for the goals set out in our climate action plan. So on the carbon side, the goals for the next 8 years for Rutgers, basically involve cleaning all of our electricity, so transitioning to carbon-free electricity, starting work, on improving energy efficiency throughout campus, and then for the next decade, getting rid of our gas-powered infrastructure, which is the costlier and harder to do bit of it. And then there are a bunch of other things, but that's sort of the big thing. And so what I'm doing at work is not necessarily what everyone can do at work, but what you all can do at work is start having these discussions and making sure that your workplace is thinking about these, and that the workforce, the workers at within your community are putting this on the table and making clear to management that it's important to them. So Alan, you look like you perhaps have something to say. Or did you just, your camera went off, so I'm not sure.